Hello everybody, welcome to Embedded ARM Dev. In this video, I'm going to go into more detail about static and dynamic linking. Also, this video will be specific to binary objects that are compiled by GCC for Linux. So let's do a quick review of linking. Remember that a symbol is just a reference to some component of an object, like a function or data. Symbols that are linked into an object file can either be resolved at compile time or at runtime, which gives us two types of linking, dynamic and static. With dynamic linking, the symbol might reference a function from some external library like libc. In this case, the compiler creates a reference to the symbol in the final object file. When the binary is loaded into memory and becomes a process, the dynamic linker loader is responsible for resolving all of those symbols so that the process knows where to find them. With static linking, all of the symbols are resolved at compile time and compiled into the final object file. A statically linked file contains all of the code it needs to execute. With statically linked files, the object code from the external library is linked into the final object. In the case of executable files, the executable contains all of the code and data it needs in order to execute. To create a statically linked binary, use the GCC static option. One disadvantage to statically linked files is that they tend to be very large. This is because they contain all of the code necessary for the executable to run. However, an advantage is that they do not depend on any shared libraries to reside on the target system in order to execute. Here we have a simple diagram showing what a statically linked executable might look like when it is loaded into memory. The printf function, which is part of libc, is actually compiled into the target executable. That is, the actual code for printf function is part of the executable and exists inside its process memory. A dynamically linked binary depends on shared objects existing on the target system that can be linked into the executable when it is loaded into memory. An advantage of dynamically linked files is that they are much smaller, since they don't contain any of the code that was linked in. They only contain references to the external symbols. However, this does require that the shared object exist on the target system so that it can be loaded into memory and linked into the executable. This diagram illustrates the basic concept for how symbols that reference shared objects are resolved at runtime. On the right side is the shared library loaded into shared memory. In this case, it is libc. Inside the shared object is the code for the function printf, which the executable needs. When the executable is loaded into memory and becomes a process, the dynamic linker is responsible for resolving any symbols the executable needs to execute. Once this has been done, inside the executable's code space, a reference to the printf function points to where it actually exists inside shared memory. Another advantage of dynamic linking is that the shared object only needs to be loaded into memory once. That way, all the processes that need to link into it will be pointed to the same location. This helps prevent wasting system memory. Before we discuss dynamic linking in more detail, let's go over a few terms. A binary is simply an executable program as it exists in file form on a disk. Technically, a binary is any object file that contains machine code, but in this discussion I'm referring to an executable file as it exists on disk. A process is a binary that has been loaded into system memory by the operating system. Loading refers to loading any shared object into system memory whenever a process that requires it is started. If the shared object is not already loaded in shared memory, then it is loaded when the process starts. Linking refers to resolving all of the references to shared objects to addresses so that the executable knows where to find them. The process of resolving the addresses of these external symbols is called binding. There are two types of binding, immediate and lazy. With immediate binding, the symbols are resolved when the process is first loaded into memory. All references to external symbols are resolved before the process starts running. This method causes the process to take longer to load, but ensures that all symbols can be resolved before handing over execution to the process. With lazy binding, the symbol is not resolved until it is first used. For example, in a process, the first time a function is called, the process will call into the linker to resolve the address for the function before calling the function. This is the default behavior for GCC on Linux. A procedure linkage table, or PLT, exists in the process memory, which helps facilitate lazy binding. The way in which lazy binding and the PLT work is a bit complicated, and I'll be covering that in a future video. So here's an example of dynamic linking with lazy binding. So here we have a binary file that is an executable file. When it gets loaded into memory, it becomes a process and has its own memory space. When the process is loaded, the loader determines that it depends on libc and also that there is a reference to printf that needs to be resolved. If libc has not already been loaded into shared memory, then the linker will load the library into memory. However, with lazy binding, the reference to printf is not resolved at load time. When the process makes the first call to printf, the linker resolves the location of printf inside libc, and the process updates the reference with the new location. So now the process knows where in shared memory that the function is. Also, note that the procedure linkage table is being used during this process, but is not shown in this diagram. Again, we'll go over that in more detail in a later video. On subsequent calls to printf, there is no need to involve the linker since the address is now known to the process. It just calls it directly. Linux uses some naming conventions for shared libraries to simplify the linking process. Each shared library has two names, a real name and a so name. The real name will be the name of the actual compiled binary. It uses the naming convention of starting with lib followed by the library name. The name will include a major and minor version and sometimes a release patch version. Most shared libraries use the convention of putting the .so first, followed by the versioning info, but some libraries like libc and libm put the .so at the very end. The shared object name, or so name, is a name that indicates the major version of the shared library. It uses the convention of lib followed by the library name, the .so extension, and finally the major version number. Note that in some cases, like libc and libm, the so name major version and the real name major version may not match. On the Linux file system, the so name is just a symbolic link to the shared library's real name. This way, if an updated version of a shared library is installed and doesn't require a major version increment, then the so name can just be made to point to the real name of the newly installed library, and the programs will link into the new one instead of the old one. So now let's do some practical demonstrations of static and dynamic linking. Alright, so right now I'm on my Ubuntu Linux VM, and I'm in my project directory, and I have a single source file. And I'll show you this source file real quick. So now if you watched my previous video on compiling, then this should look pretty familiar. This is the exact same source file. Okay, I'll go ahead and go over it quickly. First we do a printf on call hello world, which requires libc. Then this sequence right here generates a random number. Okay, and then here we make a call to square root, passing in that random number. So this will require the math library libm. And then of course we just do another print statement that prints out the random numbers and the square root of it. Okay, so that's what this source file does. So first, we're just going to compile this, but we're going to pass it the static option. Okay, so we give it the command gcc source file hello.c. We will pass it in a static. I'm actually going to give it the no position independent executable. So again, if you didn't see my video on compiling, then by default GCC compiles this to be position independent, which means it can be loaded anywhere in memory, and the code doesn't need to be fixed up. It doesn't need to have a bunch of relocations made when it's loaded into memory. So if you don't want it to be position independent, you have to pass it this option. Okay, but I would say when you're compiling an actual binary, just leave it with the default, so I wouldn't use it. But for here, we're just going to put it in for this example. Okay, and then we have to remember to link into the math library for this particular, because we're using square root. And then the output, I'm just going to make it hello. Okay. All right. So now we have the binary hello, and if I run file on the, okay, it tells us that it's 64-bit executable, and the important part for this lesson is that it's statically linked. Okay. All right. So if we wanted to try to see if there were any shared, dependencies for shared objects, remember we can use readelf, pass it the A option for all, and then we're gonna call that on hello. Then we pass it to grep and look for shared. So this should print out any shared object dependencies. Of course, this should be none, okay, which there are. So then we'll look for the interpreter, and we see that it does not require an interpreter. The next thing is, if we list it, we do a long listing. Notice the size of this. So in my previous video, I pointed this out. This is quite large, 876 kilobytes for what this file does. Okay, so that is the price for static compiling, for static linking. Okay, so one thing I want to do next is we're actually going to use a program called object dump. Okay, this is part of binutils or binary utilities, and it can do a lot of things. It is a tool for dumping objects, anything to do with binary objects. And what we're going to do is pass it the capital D option. There's lowercase d and capital D, and this stands for disassemble. So what it's going to do is take this binary and disassemble it into assembly. The lowercase d will only disassemble code sections. Okay, but the uppercase D will disassemble everything. All right. So in this case, I'm going to use uppercase D, and then I'm going to pass it the binary hello. Now, object dump puts output on the standard out. Okay, so we wouldn't use a TACO option. We would actually just redirect it. And I'm going to call this hello.dump. Okay, so this will be an assembly file based on the binary hello. Okay, and so object dump is going to disassemble it into binaries, or excuse me, disassemble it into assembly so that we can look at it. Okay, so there we go. Okay, so it looks like it's quite large. All right, so I'm just going to use gedit so it's easier to scroll. All right, so if you don't understand assembly, don't worry about this. I just wanted to show you. I'm going to do a search for main because that's where our function starts. So right here, this is the symbol for main, right? This is a symbol, and this is the address where main starts. So right here we see the address. Of course, this is the hex code for the instruction that we're looking at, and then this is the assembly, the x86 assembly mnemonic. Okay. So it's okay if you don't understand this. Don't worry about it. The reason I wanted to show you this is because you see these calls right here. So here it's calling puts. Here it calls time. Then we got srandom. So that lines up pretty well with our source file. Right? So we have our source file here. So puts, because it doesn't pass in any format specifiers, instead of calling printf, it'll just call puts. Okay, so here it calls time, then it calls srand, and then it calls rand, and then square root. So if we look at this, we kind of see that. Puts, time, srand, rand, square root, and then somewhere down here there'll be a printf, right? Okay, my mouse doesn't want to scroll. Okay, let me find it again. Okay, all right, so down here we have, there's the printf right here. Okay, so the reason I'm showing you this is because when we're looking at this statically compiled file, we notice here this is the address for this instruction right here for the actual call, and this is the address that it's going to branch to. Okay, so I'm just going to do a quick text search for that address, and it comes all the way down here. So what you notice here is that this is the symbol IO printf, and this is the address, and here's the actual code for printf. Okay, this is the actual code for printf. So we see that when we compile it statically, that the code is actually put inside this. Okay, so it's not calling to some external library at runtime. It's part of this executable. Okay, so that's all I wanted to show you with this assembly. Okay, so that's really pretty much it for static linking. The dynamic linking is a little bit more involved. So I'm going to go ahead and compile this. And so we'll call GCC on hello. Okay. We're not going to pass the static option in. We do have to link it with math. Okay. And then I'm going to output it as, but I'm going to call it dynamic so that we know the difference. Okay. So there we go. So we've got it. So now when I call file on this, it tells us that it is a shared object. Now remember, because I didn't use the no position independent executable, okay, since I didn't do that, then it makes it look like it's a shared object. Okay. If I did it again, but I put the no PIE, okay, if I recompile it with that option, and then I call file on it, all right, now it says it's an executable, so that's fine. But the important thing here is to note that it's dynamically linked. Okay. We can see here that the interpreter that it's looking for is this version. This LD is the linker loader. Okay. So this is the version. So remember when I was talking about the so name, okay, this is the so name right here. So this is the linker, so it's not a library, but it does still have a so name. So this .so.2, so 2 is the major version. Okay, so we'll take a look at this. Well, let's go ahead and look at it now. Okay, so if we look here, we see that this is the path for the linker that it's looking for. Okay, so we see that's the only thing there. If I run file on it, then what we see here is it's a symbolic link, okay, to this particular thing. Okay, so you notice here that this is the real name. This is ld-2.31.so. This is the actual binary, and then this right here is just the so name that points to this. So you could increment this 30 to 32, 33, whatever, and just keep incrementing it. As long as when you install the new version, this right here just points to the new version. Then whenever the program wants to run the linker, it'll look for this, and it'll get redirected to the most current version. Okay. So if I call file on this lib x86, and then I'll say ld-2, and that should finish it out there. So we're going to see here that's 64-bit shared object. Okay, so this is the linker / loader that we're looking at. So I just wanted to show you, the so name, which is this right here. Okay, this is the so name, and it's just a symbolic link to the actual shared object which resides on the operating system. Okay. So, all right, I'm going to keep this open because I'm going to use it. So the next thing I want to show you is we'll again call readelf on. So now we're still working with the dynamic version, and we'll pipe it to grep and search for shared. So now this should give us 2 shared libraries that it needs, libm, libc. Okay, and we'll do the same thing. And this I'm just showing you different ways to do this. Okay, you can see here that this is exactly what we were just talking about. Okay, this is the SO name for the linker loader. These are also SO names, as we'll show you in a minute. Okay, so we just need to find those. So more than likely, these are in the same directory as where, so if I do file, let me list this again. Okay, so this is where the linker loader is. It's in this directory here. More than likely, that's where these are as well. So I'm just going to go ahead and copy this. Okay. Copy it. So we'll change directory. Okay, so I'm going to go into this directory. Now there's probably a lot of stuff in here, right? Okay, so here we go. You see here that this right here is libc.so6. Okay, and when I did a search here, I found it there. So I'm actually just going to run file. So we know we're in the right directory. So I'm going to run file on this, and this will be a symbolic link because it's a so name. Okay. So when the linker, when it says, hey, I need libc.so.6, it'll get redirected to this particular file, which is libc-2.31, version 2.31. And if I call file on that, okay, then it tells us what it is, which is, of course, it's a shared object, okay, and it's looking, this is the interpreter that when it runs, it's looking for this interpreter, okay. So this is what I was looking for, though, is that it is a shared object, okay, it's a library. If I do the same thing for libm, it just so happens that these are the same version, then, you know, we get that. It's the same thing, but this is libm. Okay. So the so name for libm, okay, there's all this, so this is the so name. So this right here is the so name. This is what it's going to look for. And it's just going to get a symbolic link to libm 2.31, okay, which is this right here, what I dumped. Okay. All right, and so finally, I think we don't need this anymore. So we're going to do the same thing. I'm going to call object dump, capital D. And for this one, we definitely need the capital D. And I'll show you why in a minute. So we're going to call it on hello dynamic. And okay, so this is object dump puts the output on standard out. Okay, so we're going to call this hello dynamic dot dump. Okay, so it's there, and let's make sure that there's something to it. Okay, there we go. So notice this. This was the dump of the static compiled code. Okay, so this is assembly source code, right? But look how large it is. And this is the dump of the dynamically linked one, so it's significantly less. Okay, so I'm just going to go ahead and open it in gedit. Okay, so we can look at this. So again, this is x86 code, and don't worry if it doesn't make sense. Go down to main. All right, so here's our main. Okay, you can see this is the address where main, the symbol of main starts, and you've got similar things. Now, what's interesting here that's different than the static. Okay, so let's do, so we can compare. Let's also do the static one. That was hello.dump. What was it? Hello.dump. So we'll gedit. Okay. All right. So I just want to be able to compare these. Something is wrong. Where's my main? Okay, I think it's just slow. It's going slow for some reason. All right. Okay, so here we go. So notice these are different addresses. I'm going to move this to the left side. So here we got 1 delta 3 5. Here it's a different address. Okay, of course that's just because they're completely different binaries. But so this is static, and so you notice that when it calls this here, it just gives the name of the actual. So this is static. It gives the name of the actual function in this address right here. But in the dynamic, notice that it calls an address, and it says PLT, which stands for procedure linkage table. And if you notice, you come down here, all of these are in the procedure linkage table. Okay. And so also what you notice is that 4010A0, 4010E0, D0, so you know that these are all very close to each other. Okay. So what happens is when it's actually going to call puts, this means it's going to go into the procedure linkage table. Okay. So if I'm going to copy this address here. We'll just go up to the top. All right. So you can see here that this is where So the procedure linkage table is a section, and we'll get into that in a different video. Don't worry about it right now. But all you need to know is this right here is the procedure linkage table. And so puts is like right here, and then you got printf is right here, and then sran. And so we'll cover this in more detail, but you see here that instead of code, like actual code for these functions, okay, this is a stub that basically is the start of how the linker will resolve where a printf actually is, and then go to it, branch to it. Okay, so when we actually go into this in later videos, I'm going to use ARM because I'm a little more familiar with it and I can explain it better. So that's basically it for dynamic linking. One other thing is, like, the last thing we want to do is compare. So here we got the dynamically linked hello, which is 16 kilobytes, and we've got the statically linked hello, which is 876 kilobytes. So I don't know what that is. That's like 20 times larger than, so it's definitely better size-wise to use the dynamic linking than it is the static linking. Okay, so that's it for dynamic linking. So let's summarize what we've talked about in this video. With dynamic linking, symbols from external libraries are linked in by the dynamic linker at runtime. The executable depends on the shared object or shared library residing on the target system in order to execute. With static linking, the symbols from the external libraries are compiled into the final object at compile time. In this case, the executable does not depend on anything residing on the target system in order to execute. We talked about shared library naming conventions, in which there's a real name and a so name. The so name is simply a symbolic link to the real name. That's it for this video. I hope you found it useful. Leave any comments or questions that you have, and we'll see you in the next time.